Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as we do every night during Advent of Code, we're going to be trying to solve these puzzles in C++. Thank you for joining me, whether you're joining on the live stream on Twitch or you're watching the stream replays later on YouTube. We're glad to have you here. If you're watching on Twitch, you can check the channel description, and there you are going to find links to my YouTube channel with all the stream replays, and also a link to my GitHub repo where we upload all of the code that we write. If, on the other hand, you're watching on YouTube, just check the video description right down there, and you're going to find links to that Twitch channel for live streams, and also, once again, to that GitHub repo where we put all of the code that we write. So we are getting in to the home stretch of Advent of Code. We are waiting for the day 20 puzzle drop tonight. Last night, day 19, was definitely the most time that we've spent on any one of these. Probably the most complicated puzzle so far. Involved a lot of thinking about 3D geometry and stuff, and then, we had an algorithm that worked but was really slow and trying to tune that for performance. And, we had a lot of fun doing that. And actually, I did a little more even after last night's stream. I went a little farther and I implemented in my dimension grid geometry library this entity called rotation, and it works, it still only allows like integer coefficients and, can only do like 90-degree rotations because, this is, a grid geometry library, not an actual continuous geometry library. But it does work by basically having a rotation matrix and doing matrix multiplication with vectors and all that good stuff. So I went back and modified the day 19 solution to use all that good stuff for rotations that we added to the dimension grid library. And if you're interested in that, that is all up in the GitHub repository now, so you can take a look at that. But that makes the, the actual solution for day 19 a bit cleaner because, the actual geometry stuff is all handled by that library. So for tonight, we'll see if we have another one like last night that was, a pretty big challenge that takes a long time. Who knows? Maybe, maybe not. But for now, we just have this bare bones kind of skeleton of a program here. Kind of the same thing that we start off with every night. We have a main function that returns 0. Doesn't do anything besides that, but I have included the check and IO libraries that I wrote that we use pretty much every night. And I've set up this Bazel build file that tells the build system, Bazel, that we're using, how to build this, what the source code files are and what its dependencies are. So, we use check for assertions, we use IO to read files and parse them. And having those pre-written, saves us some time and aggravation when we get started on the puzzle. So, yeah, we are definitely in the stretch of the, more challenging puzzles now. Like I said, last night was probably the hardest so far this year. But, it was fun. We didn't get stuck for too long besides, me trying to, bang my head figuring out the geometry of all the rotations. But I still think it was pretty interesting. So we'll see how we do tonight. We've got about 1 minute until tonight's puzzles drop. Before I started this stream, I was just reading this article in the MIT Technology Review about Advent of Code. And, the people who love doing it. And it is, there's people of all different skill levels, all different experience, just coming together to have fun solving these puzzles. It's pretty cool. And Eric Weistel, the guy who runs it and designs all of the puzzles, really gives us this great gift every year. It is a lot of fun. So, definitely appreciate that. That's why also, at AOC++, Advent of Code++, you can contribute here to, the cost to keep it running, and to say thank you. I think that's a great thing to do if you're having fun with this year's puzzles. But let's get started. Okay, trench map. The scanners fully deployed, you turn their attention to mapping the floor of the ocean trench. Get back an image from the scanners. It seems to be just random noise. So you can combine an image enhancement algorithm with the input image and clean it up a little. Okay. So we've got dots and hashes. First section is the image enhancement algorithm. It's normally given on a single line, but has been wrapped to multiple lines for legibility. Okay, one big line of that. Second section is input image, a two-dimensional grid of light pixels and dark pixels. The image enhancement algorithm describes how to enhance an image by simultaneously converting all pixels in the input image into an output image. Each pixel of the output image is determined by looking at a 3x3 square of pixels centered on the corresponding input image pixel. Hey, 2D grid geometry, who'da thunk it? So to determine the value of pixel at 510 in the output image, 9 pixels from the input image need to be considered. Okay? These 9 pixels are combined into a single binary number that is used in index in the image enhancement algorithm string. Okay. You combine these. Turning dark pixels, dots into 0, and light pixels, hash marks into 1, we get a binary number. This, which is 34 in decimal. The image enhancement algorithm string is exactly 512 characters long, enough to match every possible 9-bit binary number. Okay. All right. Through advances in imaging technology, the images being operated on here are infinite in size. Every pixel of the infinite output image needs to be calculated exactly based on the relevant pixels of the input image. The small input image you have is only a small region of the actual infinite input image. The rest of the input image consists of dark pixels. Okay. For purposes of the example, to save on space, only a portion of the infinite-sized input and output images will be shown. Okay, so we assume that everything out of range is a dark pixel, a 0. So we can run the image enhancement program multiple times. Okay. Start with the original image and apply the enhancement algorithm twice and determine how many pixels are lit in the... Be careful to account for infinite size, determine how many are lit. Okay. I am going to... Because it can expand in positive and negative and go in infinity directions, the way that I am going to choose to do this is a sparse representation where we save, like, you know, every coordinate and... yeah, we'll do that. So we've got our input. Let's take a look at our day 20 input. Okay. So the image is quite a bit larger than the one in the example, but we've got our program, we've got our image. So all right, let's get to it. First thing, we'll just read the input. We'll do a vector of strings for all the lines. Use our read lines from file function with the first line of the program, and then we expect the first line. I'm gonna open this in Nano because I just think that each one of these is. You know what I'll bet is we have 100 by 100 input image. Yeah. Okay. So for the first one, we will. No, not vector. We're just going to make a vector of bools, we're going to say it's going to be we'll call that parse enhancement program. And then for characters, so we'll have, our vector of bools for the program. And then for characters in that representation of the program, we will switch on what the character is. So if it is a hash mark, switch on C, case hash mark, then we will put true on that. And if it is a dot, then it is a dark pixel, and that will be false. Otherwise, something is wrong, and it's an unexpected character, so we'll check fail there. Okay, so that's our program. And then for our representation of an image, we will, for now, I'm just going to make it a struct. Yeah, maybe make it a class. Actually, do a little more encapsulation there. Actually, structs and classes are the same in C++. Literally the only thing that differs between them is that structs default to public visibility and classes default to private visibility. But of course, you can put public and private labels wherever you want in either one. And they are truly exactly the same in C++. But we'll say private. We're going to use a flat hash set to represent light pixels. And we will use our, we're going to use our grid2 library because it's going to give us an easy way to represent points. That 2D geometry library that I wrote previously. And for the sake of brevity, I'm just going to be using the whole namespace for grid2. So we'll say a flat hash set of points is going to be bright pixels. So first thing we can do for the image is we can parse from the input. So we will say image. We'll just do it in the constructor here. Yeah. These are int64, coordinates are int64s in our library, so we'll just say y equals 0, y is less than rep.size plus y. And then for 64t, x is 0, x is less than rep at y. Now all the lines are the same length. They should all be 100 characters, it looks like. But just to be extra safe, I'm doing it this way. And then we will switch on the value, the actual character there at yx. If it's a hash mark, then it is a bright pixel. And we are going to put it in the set of bright pixels. So we'll say bright pixels in place, xy. If it is a dark pixel, we won't do anything, but we know it's valid. But if it's something different, then something is wrong, and we will check fail there. Okay, so that should parse our image. And then for a given output pixel, let's see here. So I'm looking back here. Just I'm starting to think ahead to the algorithm and think how we deal with if we have this infinite image. So the interesting thing here is that our enhancement, the first character of our enhancement program is a hash mark, which would seem to indicate that if you had all dark pixels together, then you would wind up with all light pixels next round. So if we keep track of just bright pixels each time, then oh boy. So what I'm going to do is I'm going to add a field to this class called inverted. And for now it's going to be false, but it basically means that, you know, bright is dark and dark is bright, because the actual image is infinite in all dimensions, but the fact that the very first character of this program, meaning the one that corresponds to all dark pixels, will flip everything to bright pixels, and then the last character of the program, which corresponds to a grid of 3 by 3 bright pixels, flips that to dark pixels, means that anything that is outside of the entirety of the grid, of the inner part of the image that we're working on, flips back and forth between bright and dark, and we can't count, you know, an infinite number of bright pixels the first time that we apply it, and then flip back to an infinite number of dark pixels the second time we apply it. So that's what that inverted is doing. That is a tricky thing about this input. I wonder if everybody got something like this for their input, or we just happened to get unlucky and get something complicated, but we shall see. So the thing to do now is we'll write this apply program now, which will take that input program and produce a new image with the result. Yeah, you can just make that default constructible. It's fine. Okay, so for this result, first thing we're going to need to do is look at if we're not inverted and the the first element of the program, the element that corresponds to all dark pixels, would flip things to light pixels, then result is going to be inverted. Otherwise, if we are inverted, and the back element, which corresponds to all bright pixels, is that it's dark, would flip back to dark. Why is that? You're not liking that? Oh, it's just else if. Sorry. Then the result should be false. And okay. That should be fine. I think we might have to come back to that flipping logic, but I think I hope we are okay. So we need to so basically everything that's outside that is beyond 1 away from a pixel that we know is in this bright pixel set, or if it's inverted, the dark pixel set will be covered by this. But now we need to find the actual kind of bounds for us to look over. So we have these min dimensions and max dimensions functions, which are going to give us kind of like the bounding rectangle for all the pixels here. So we can run that over our bright pixels container. Do that over our bright pixels container, and then we'll write this value for pixel method here, and this is going to calculate those 9 binary digits around a particular pixel. So basically, we will say dy for -1, 0, and 1, for 1 above, at the same level, and below, and same for dx. And that should be in the right order, so we'll say value equals value left shifted by 1, or with bright pixels dot contains p plus vec with a vector with those dx and dy. Okay. And then if this is inverted, we have to flip the whole thing. So if inverted, then value equals not value, and we're just going to mask out the lower 9 bits. Okay. So that should give us the value in the program. And this, we should check value greater than or equal to 0 and value less than 512 at that point. Okay. So we've got the value for pixel, which gives us a place to look it up in the program. And then so the actual min and max, we should go one. We should go one to the left and up from the actual min, and one to the right and down from the actual max to capture everything that includes a pixel that we actually know about in our grid. So I'm going to go ahead and say then we can similarly do plus vec dot dx equals 1 dot dy equals 1. Okay. So we've got our bounding box with those min and max points, and we've got our value for pixel function that we can use to look things up. So now we will say for points in that range, so we'll loop over y into x. We'll say y equals min dot y. Y is less than or equal to max dot y plus y. Do something very similar in the x dimension here. At some point, maybe we'll add something to the geometry library that makes doing this kind of iteration over a bounding box easier, but for now, we're just doing this. So whether the next pixel is right is going to be program at value for pixel that point with that xy. But if bright and not result dot inverted. So if it's bright and it's not inverted, or not bright and result dot and the result is inverted. Actually, so I think we do this if bright XOR result inverted. So if it is bright and the result's not inverted, then we'll set it. Or if it's dark and the result is inverted, we'll set it. So and then return result. Okay. And then we need to know how many pixels are lit in the resulting image. So so it better not be inverted, because if it's inverted, that infinite space off the part that we're tracking is all going to be lit, and there will be an infinite number of lit pixels. Otherwise, we can return bright pixels.size. Okay, so now we just get down and write the main part of the program. We will say we're going to split that input by the empty lines the front part is going to be the program. We'll check that it's just one line. Program equals that parse enhancement program from that first string. And just going to double check that it has exactly the size that we were promised of 512. Okay. Then I'm going to say image. Image. We'll parse that from the other set of segments. And then we are supposed to apply it twice, so we'll just say for int iteration equals 0, iteration less than 2, plus iteration image equals image dot apply program. And at this point, we can print out the number of pixels that are lit. So we need to we depend on the strings, flat hash set, and grid2 libraries. So we need to add all that stuff to our dependencies in the build file before we can build this again. Flat hash set and strings. Just going to copy paste from a previous day for speed here. Okay, let's try and run our program on our puzzle input here for day 20. Okay. Failed to build here. I'll bet it was probably this. So that in place, there's not a constructor that can actually forward to there. So let me try doing that. Okay, it says 5,846 pixels are lit. Let's see if that is correct. All right, rank 500 today. You still can't quite make out the details on the image. Maybe you just didn't enhance enough. If you enhance a starting input image in the above example 50 times, okay, so we just need to apply the program 50 times. Well, let's see if this solution blows up or not, but I'm just going to change that to 50 and we'll see. Okay. That still went pretty darn quickly. Let's see if that works. Bomb! 375! That might actually be our best result so far this year. Let's check personal stats here. Yeah, 375 for the second star. All right. So, tonight's went obviously a lot faster than last night's. It was helped a lot by, well, it was helped some by having a pre-written geometry library, although not as much as it necessarily would have been. I mean, sure, we, used this, pixel addition and this bound box finding and everything. But honestly, that was stuff that we could have whipped up pretty quickly if we hadn't already written it. I think the main tricky thing about this is that you have an infinite space of pixels, and that big, vast sea of pixels out from your initial image can flip each iteration. So they're not always going to be dark, as we saw. In our program, the big, ocean of pixels surrounding would flip back and forth between back and dark with between light and dark with every iteration, which is why we had to keep track of inverted, as we had here. That was, I think, really key. So, yeah, I think that, we saw that by looking at the program right away. Everything else was relatively straightforward. We built up, this binary number just by going over those 9 pixels in a square. And yeah, it just, yeah, I really think the only tricky thing was just the inverting of, the sort of the canvas. Um, but everything else worked fine. And I think the sparse representation with where we just put everything in a set of points was probably the right way to go. I think that you can definitely design kind of a 2D grid that accommodates growing in multiple directions, but the data structure is a little bit tricky. So just keeping a sparse representation, like just a set of the on pixels or the off pixels if it's inverted, I think was definitely the simplest way to go here. And we got our solution pretty fast. So yeah, feel really good about tonight's result. Thank you all for watching. I hope that you had fun as well. Once again, if you are watching on Twitch, check the channel profile. There you will find links to my YouTube channel, which has all the stream replays, as well as the GitHub repo, which has all the code that we write. If, on the other hand, you're watching on YouTube, just check that description right down there. You're going to find links to that Twitch channel with the live streams, and once again, the GitHub repo with the code. Thank you very much for watching, everyone, as we go into the home stretch of these Advent of Code puzzles. I hope you had fun tonight, and I hope to see you again tomorrow. Bye-bye.